Every planet in the solar system inherited its spin from the same cloud of gas and dust, pulled by the same gravity, turning the same direction. Venus spins the other way, and tonight we are going to find out what could possibly override a force as fundamental as gravity itself. Keep tonight open, because the answer involves a 4.5 billion year fight between three invisible forces, and the winner is the last thing you would expect. But first, find a window that faces west. If the timing is right and the season is kind, you'll see it. A single point of light, low on the horizon, appearing before any star has the courage to show itself. Brighter than anything else in the evening sky. Steady, no flicker, no twitch. Just a calm, clean glow settling into the dusk like it belongs there. That is Venus, the evening star, and for most of human history, that is all anyone needed to know about it. A beautiful light, a reliable companion to sunset. Shepherds used it to mark the end of the working day. Sailors used it to find west when the compass was still centuries away from being invented. Poets gave it every name they could think of. The Romans called it Venus. The Babylonians called it Ishtar. The Maya tracked its cycles with such precision that their observations, recorded over 1,000 years ago, are accurate to within 2 hours per century. Everyone who looked up saw the same thing, a wandering light that never quite behaved like the stars around it. It appeared in the evening, vanished, then reappeared in the morning a few weeks later, as if it had walked around the back of the sky. Of course, we now know why. Venus orbits closer to the sun than we do. It never strays far from the sun's glare in our sky, so it is always either leading the sun at dawn or trailing it at dusk. Never overhead at midnight, never far from the horizon, always tethered to the twilight. But here is what makes Venus interesting in a way that goes far beyond its beauty in the evening sky. Venus is, by nearly every measure we care about in planetary science, almost identical to Earth. Let that comparison settle in for a moment, because the similarities are striking. Venus has a radius of 6,051.8 kilometers. Earth's radius is 6,271 kilometers. That makes Venus about 95% of Earth's size. If you held the two planets side by side, you would struggle to tell them apart by shape alone. The difference in diameter is roughly the distance from New York to Denver, significant on a road trip, negligible on a planetary scale. Mass follows a similar pattern. Venus weighs in at 4.867 times 10 to the 24th kilograms. Earth is 5.972 times 10 to the 24th. So Venus carries about 82% of Earth's mass. Again, close, remarkably close. Close enough that the gravity you would feel standing on the surface of Venus would be about 90% of what you feel right now, wherever you are. You would feel lighter, but not dramatically so. A person who weighs 150 pounds on Earth would weigh about 136 pounds on Venus. You would notice, but you would not float. Both planets are rocky, both formed from the same region of the solar nebula, built from the same raw materials, in roughly the same neighborhood, roughly 4.5 billion years ago. They share similar bulk compositions, iron cores, silicate mantles, thin crusts of rock. If you were designing a solar system from scratch and someone handed you the blueprints for Earth and Venus without labels, you might reasonably assume they would turn out more or less the same. And for a long time, people assumed exactly that. Through the early 20th century, Venus was imagined as a lush, tropical world. Its thick clouds, which hide the surface completely from view, were taken as evidence of a warm, wet atmosphere. Perhaps oceans, perhaps jungles. Science fiction writers populated it with swamps and dinosaurs and rainstorms, It was Earth's younger sibling, a little closer to the Sun, a little warmer, but fundamentally familiar. The clouds kept the secret well, because beneath that bright, featureless veil, Venus is nothing like Earth. The surface temperature sits at 465 degrees Celsius, hot enough to melt lead. The atmospheric pressure is 90 times what we experience at sea level, equivalent to being a kilometer underwater in Earth's ocean. The air is almost entirely carbon dioxide, laced with sulfuric acid clouds, but none of those differences, as dramatic as they are, is the strangest thing about Venus. The strangest thing about Venus is the way it spins. Venus rotates backward. Every other planet in the solar system, with one partial exception we will get to later, spins in the same direction, counterclockwise, when viewed from above the North Pole. The Sun spins that way, Earth spins that way, Mars, Jupiter, Saturn. All of them turning the same direction, like gears in a machine that were all set in motion by the same hand. Venus turns the other way, slowly, almost impossibly slowly, and in the wrong direction. Tonight, we are going to find out why. To understand why Venus spinning backward is so strange, we first need to understand why planets spin at all. And to understand that, we need to go back to the very beginning. Not the beginning of Venus or of Earth, but the beginning of everything in our solar system. 4.5 billion years ago, there was no sun, no planets, no moons. There was only a cloud, a vast, cold, diffuse cloud of gas and dust, hanging in the space between stars, mostly hydrogen, some helium, a scattering of heavier elements forged in the cores of stars that had already lived and died. Carbon, oxygen, silicon, iron, all of it drifting, all of it cold, all of it, for the moment, going nowhere in particular. But the cloud was not perfectly still. Nothing in space ever is. It had a slight rotation, not fast, not dramatic, just a gentle, almost imperceptible drift. If you could have stood inside it and watched a single grain of dust, you would have seen it moving, ever so slowly, in a lazy arc. This matters. This matters enormously, because what happened next is governed by one of the most reliable rules in all of physics. Conservation of angular momentum. The name sounds technical, but the idea is something you already understand intuitively. You have seen it happen. You may have even felt it in your own body. Think of an ice skater. Picture a figure skater in the middle of a spin. She begins with her arms stretched wide, turning slowly on the ice. Then she pulls her arms in, close to her body, and she speeds up, dramatically. The spin becomes a blur. She did not push off again. She did not kick. No new energy entered the system. She simply moved her mass closer to the center of rotation, and the spin responded by getting faster. This is conservation of angular momentum at work. The total amount of rotational motion in a system stays the same, unless something from outside pushes on it. So if you shrink the system, if you pull the mass inward, the rotation must speed up to compensate. The total amount of spin is conserved. It has to go somewhere. Now apply that same principle to our cloud of gas and dust. That enormous, cold, diffuse cloud with its barely perceptible rotation. Something disturbs it. Perhaps a shockwave from a nearby supernova. Perhaps the gravitational tug of a passing star. Whatever the cause, parts of the cloud begin to collapse inward under their own gravity. And as the cloud collapses, the same thing happens that happens to the skater. The material draws inward. The rotation speeds up. What was once a barely detectable drift becomes a definite spin, and the cloud begins to flatten. This flattening is important. It happens because the spin creates a preferred plane. Material falling inward along the axis of rotation can collapse freely, but material in the plane of rotation is supported by its own centrifugal motion. It cannot fall inward as easily, so the cloud squashes. It becomes a disk, a protoplanetary disk, spinning around a growing concentration of mass at the center. That central concentration will become the Sun. And here is the key detail. Everything in the disk is rotating in the same direction. The same direction the original cloud was drifting, only faster now. Every particle of gas, every grain of dust, every pebble and boulder that will eventually become a planet is orbiting the young Sun in the same direction. Counterclockwise, as seen from above what we now call the North Pole of the solar system. This is the inheritance. The Sun spins counterclockwise because the cloud spun that way. The planets orbit counterclockwise because they formed from that same spinning disk. And the planets themselves spin counterclockwise on their own axes because they assembled from material that was already moving in that direction. Think of it this way. Imagine an eddy in a river, a slow, wide spiral of water turning gently in one direction. Now imagine small whirlpools forming within that larger eddy. They will tend to spin the same way as the larger flow around them, because they are made from that flow. They inherit its direction. Planets work the same way. As the protoplanetary disk evolved, small clumps of material began to stick together. Dust grains became pebbles. Pebbles became boulders. Boulders became planetesimals, objects a kilometer across or more. And these planetesimals continued to collide and merge, growing larger with each collision, sweeping up the material around them. Each collision, on average, added more angular momentum in the same direction, because the material being swept up was already orbiting the same way. The growing planet was like a snowball rolling through snow, and the snow was already moving in the same direction as the snowball. Each addition reinforced the existing spin. By the time the process was complete, you had a set of planets, each orbiting the Sun in the same direction, each spinning on its own axis in the same direction, each carrying the angular momentum of the original cloud, concentrated and amplified by billions of years of gravitational collapse. This is the rule. This is the expectation. This is what the physics demands. Mercury spins prograde. Earth spins prograde. Mars spins prograde. Jupiter and Saturn and Neptune all prograde. All counterclockwise from above. All faithful to the original rotation of the cloud that made them. The inheritance is clear. The pattern is consistent. The physics is clean and well understood. Every planet in the solar system should spin counterclockwise. And then there is Venus. Venus rotates clockwise, retrograde, against the flow, against the inheritance, against everything the physics of planet formation would predict. Something happened to Venus. Something broke the rule. But before we can investigate what, we need to understand how we discovered the anomaly in the first place. Because for most of human history, no one knew which way Venus was spinning. No one could see through the clouds. Until 1962. The Goldstone Deep Space Communications Complex sits in the Mojave Desert, about 40 miles north of Barstow, California. In 1961, it was already one of the most sensitive radio installations on Earth, built to communicate with spacecraft traveling to the Moon and beyond. But in that year, a team of researchers decided to use it for something different. They pointed it at Venus. Radar astronomy in 1962 was still a young science, barely a decade old. The handful of people who practiced it occupied a strange middle ground between radio engineering and planetary science, and neither community fully claimed them. They built their own equipment, wrote their own signal processing code on room-sized computers, and spent long nights nursing transmitters that ran at the edge of their tolerances. The culture was improvisational, intimate. When something interesting appeared in the data, you didn't send an email. You walked across the room and tapped someone on the shoulder. The idea was straightforward in concept, though extraordinarily difficult in practice. Send a radar pulse toward Venus. Wait for it to bounce off the planet's surface and return to Earth. Then study the echo. The sheer distance involved made the experiment an exercise in patience. A radar pulse aimed at Venus, even at the planet's closest approach to Earth, takes about 4.5 minutes to cross the gap, reflect off that cloud-shrouded surface, and return. 4.5 minutes of silence in a concrete room in the desert, listening to static, waiting for the faintest possible echo. And faint is an understatement. The return signal was billions of times weaker than what was transmitted. Extracting it from the background noise required hours of observation. The echoes stacked and averaged again and again, until a pattern emerged from the randomness like a face slowly surfacing in dark water. Radar had already been used to measure the distance to Venus with remarkable accuracy. But distance was just the beginning. The echo contained something else, something subtle, something that, if you could measure it precisely enough, would tell you how fast the planet was rotating and in which direction. The technique relies on the Doppler effect, the same phenomenon that makes an ambulance siren sound higher in pitch as it approaches and lower as it moves away. When a radar signal bounces off a spinning planet, the echo from the side of the planet rotating towards you is shifted to a slightly higher frequency. The echo from the side rotating away is shifted lower. The spread of frequencies in the return signal tells you how fast the surface is moving and in which direction. Richard Goldstein, a young researcher at the Jet Propulsion Laboratory, and Roland Carpenter, working with data from both Goldstone and the enormous Arecibo radio telescope in Puerto Rico, set about analyzing the radar echoes from Venus during its close approach to Earth in 1961 and 1962. They expected to find a planet spinning prograde. Every model of planet formation predicted it. Every other planet they had measured spun that way. Venus, Earth's twin in so many respects, should follow the same pattern. The only real question, they thought, was how fast. Some astronomers had suggested Venus might be tidally locked to the Sun, showing one face permanently, the way the Moon shows one face to Earth. Others expected a rotation period of a few days, maybe a few weeks. There was no consensus, because the clouds made direct observation impossible. But almost no one expected what the radar revealed. The Doppler broadening was wrong. Not wrong in the sense that the measurements were bad. The measurements were clean, repeatable, and clear. Wrong in the sense that the frequency shift was on the wrong side. The limb of Venus that should have been approaching, based on prograde rotation, was receding. The limb that should have been receding was approaching. The entire Doppler signature was inverted. Venus was spinning backward. Goldstein and Carpenter published their findings in 1963 in a paper in the Astronomical Journal. The language was measured, as scientific papers tend to be, but the implication was extraordinary. Here was a planet, Earth's nearest neighbor, its closest sibling in size and mass and composition, and it was rotating in the wrong direction. The angular momentum it should have inherited from the protoplanetary disk had been not merely reduced but reversed. The reaction in the planetary science community was, at first, cautious. Radar astronomy was still a young field. The measurements were difficult. The signal-to-noise ratios were thin. Could there be an error? Could the analysis be flawed? But within a few years, additional observations from multiple facilities confirmed the result. Venus was indeed rotating retrograde, and it was doing so extremely slowly. Within 2 years, the enormous dish at Arecibo, Puerto Rico, joined the effort. Arecibo's 1,000-foot reflector, built into a natural limestone sinkhole in the Caribbean hills, was the largest radio telescope on Earth. Its collecting area dwarfed Goldstone's, and when its operators turned that vast bowl toward Venus, the retrograde signal came through with unmistakable clarity. What had been a tentative finding supported by painstaking statistical arguments became, in Arecibo's data, simply obvious. The planet was rotating the wrong way. No amount of reprocessing or alternative interpretation could make the signature disappear. The sidereal rotation period, the time it takes to complete one full turn relative to the distant stars, was approximately 243 Earth days. 243 days for a single rotation. To put that in perspective, Earth completes one rotation every 23 hours and 56 minutes. In the time it takes Venus to turn once on its axis, Earth has spun around 243 times. You could live through an entire pregnancy, from conception to birth, and Venus would not yet have completed a single day. And it was turning the wrong way. This was not a minor anomaly. This was not a small deviation from the expected pattern, the kind of thing you could explain with a statistical fluctuation or a rounding error in the models. This was a fundamental violation of the inheritance rule. Every planet should spin prograde. Venus spins retrograde. Something happened to this planet that did not happen to any of its siblings, and whatever it was dramatic enough to reverse the rotation of an entire world. The discovery also raised a second, quieter puzzle. It was not just that Venus was spinning backward. It was spinning backward slowly, incredibly slowly, as if whatever process reversed its rotation also nearly stopped it. Venus is not whipping around in the wrong direction. It is barely turning at all. It is the slowest rotating planet in the solar system, retrograde or otherwise. Goldstein and Carpenter had opened a door that planetary science has been walking through ever since. What could reverse a planet's spin? What could slow it nearly to a stop? And why Venus, of all the worlds in the solar system? The data would eventually sharpen. The rotation period refined to 243.025 Earth days. But the central mystery remained, and remains to this day. We know the numbers now. We know them with extraordinary precision, and every one of them is strange. Let's lay out the numbers. All of them. Because Venus, once you start looking at the data, does not just break one expectation, it breaks several. And each number, taken on its own, is peculiar. Taken together, they describe a world that seems almost deliberately contrary. Venus completes one full rotation on its axis every 243.025 Earth days. That is its sidereal day, measured against the fixed background of stars. And the rotation is retrograde, meaning clockwise when viewed from above the North Pole. We have established this. But sit with the number for a moment. 243 days. That is roughly 8 months. 8 months for the planet to turn around once. If you stood on the equator of Venus and watched a single star directly overhead, you would have to wait 243 Earth days before that same star returned to the same position in the sky. In that time, on Earth, summer would have become winter, or winter would have become summer. You would have celebrated a birthday, paid rent 8 times, watched the leaves change color and fall. Now here is where it gets genuinely strange. The orbital period of Venus, the time it takes to complete one trip around the Sun, is 224.7 Earth days. That number is shorter than the rotation period. Venus's year is shorter than its day. On Earth, this relationship is so lopsided in the other direction that we never think about it. Earth's day is 24 hours. Earth's year is 8,766 hours. The year contains 365 days. It is not even close. On Venus, the planet completes an entire orbit around the Sun before it has finished turning around once. Venus will have a new year before it has a new morning. The year ends, and the same day is still going. This is, as far as we know, unique in the solar system. No other planet has a day longer than its year. There is another number that matters here, and it requires a brief distinction. The sidereal day, those 243 Earth days, measures the rotation against the stars. But the solar day, the time from one sunrise to the next, is different, because while Venus is slowly rotating, it is also orbiting the Sun. The combination of those two motions means the solar day on Venus is 116.75 Earth days, roughly 117 Earth days from one sunrise to the next. Still extraordinarily long, still nearly 4 Earth months between one dawn and the following dawn, but shorter than either the sidereal day or the year, because the orbital motion partially compensates for the slow rotation, and because the rotation is retrograde, the Sun rises in the west on Venus. Think about that for a moment. Every sunrise you have ever seen has come from the east. Every sunset has fallen into the west. This is so fundamental to human experience that we built our maps around it. East is where the day begins, west is where it ends. On Venus, the Sun climbs out of the western horizon, crosses the sky over the course of about 58 Earth days, and sets in the east. Everything is reversed. The compass roses backwards. The axial tilt tells the same story from a different angle. Earth's axis is tilted at 23.4 degrees from the vertical of its orbital plane. This tilt gives us our seasons. Venus's axis is tilted at 177.36 degrees. That is nearly upside down, almost exactly inverted. If you tilt a spinning top past 90 degrees and keep going until it is nearly flipped over, the top appears to be spinning the other way. That is what Venus looks like from above. Its north pole points roughly where its south pole should be, and the direction of rotation, viewed from the conventional top of the solar system, is reversed. And finally, the speed. At Venus's equator, the surface moves at approximately 6.5 kilometers per hour relative to the planet's center. That is a leisurely walking pace, a casual stroll. You could keep up with the rotation of the planet by simply walking in the opposite direction. Earth's equatorial velocity, by contrast, is roughly 1,770 kilometers per hour. Fast enough that if the atmosphere were not moving with the surface, you would experience winds of over 1,000 miles per hour. Venus turns so slowly that its rotation is almost an afterthought. A planet the size of Earth, barely spinning, moving its surface at walking speed, in the wrong direction. These numbers are clean. They are well measured. They have been confirmed by decades of radar observations and spacecraft visits. They are not in dispute. What is in dispute is how any of this happened. How do you take a planet that should spin prograde, that should turn once every several hours like its siblings, and leave it barely rotating, nearly inverted, with its days longer than its years and its sunrises in the west? Something broke Venus, something fundamental, and the search for that something has occupied planetary scientists for more than 60 years. The solar system did not begin quietly. 4.5 billion years ago, where you now see orderly planets tracing clean ellipses around the Sun, there was a construction site. Billions of rocky fragments, some the size of mountains, some the size of small countries, all orbiting in roughly the same direction, all slowly accumulating into larger and larger bodies through a process called accretion. Think of it like a demolition derby, where the cars occasionally fused together instead of flying apart. Over millions of years, the winners of these collisions grew. They swept their orbital neighborhoods clean. They became the planets we recognize today. And this phase lasted far longer than you might expect. For perhaps 100 million years after the Sun first ignited, the inner solar system remained a crowded, volatile place. Dozens of planetary embryos, some the size of Mars, others smaller, all of them circling the young Sun on orbits that were not quite stable, close enough to nudge one another, close enough to trade gravitational whispers across the void, slowly warping each other's paths until, inevitably, those paths crossed. The numbers themselves tell a story. Simulations suggest that somewhere between 20 and 50 of these embryos once occupied the region where 4 rocky planets exist today. 20 to 50 small worlds, all jostling for space in a zone not much wider than the distance from the Sun to Mars. You can imagine the mathematics of it. With that many bodies in that little space, collisions were not rare accidents. They were the primary mechanism of growth. Planets did not form by gently collecting dust. They formed by swallowing each other, and each collision was singular. Each one happened at a particular angle, a particular speed, with a particular ratio of masses. Some were glancing blows that sprayed debris into orbit. Others were more direct, the two bodies plunging together and fusing in a matter of hours, their combined heat so intense that the resulting world became an ocean of magma thousands of kilometers deep. There was no template for these events, no standard outcome. Every encounter rolled its own dice. But the final stages of that process were not gentle. The last few mergers involved bodies that were already enormous, protoplanets the size of Mars, or larger, still drifting on slightly different orbits, still capable of crossing paths with one another. And so, when scientists first confronted the puzzle of Venus's backward spin, the most intuitive explanation was also the most dramatic. What if something hit it? Not a small something, a world. The idea goes like this. Late in Venus's formation, when the planet was nearly its current size but still growing, a massive body, perhaps comparable to Mars, roughly half the diameter of Venus itself, struck the young planet at just the right angle. A glancing blow, not head-on, which would have been absorbed more symmetrically, but off-center, delivering a tremendous amount of angular momentum in the process. Angular momentum is what determines how something rotates. It depends on mass, speed, and how far that mass is from the center of rotation. When you push a merry-go-round, you're adding angular momentum. When a figure skater pulls their arms in, they're not adding angular momentum, but they are concentrating what they already have, which is why they spin faster. Now imagine pushing a merry-go-round that's already spinning one direction, but you push it the other way. If you push hard enough and long enough, you can slow it down, stop it, and eventually reverse it. That, in essence, is what the giant impact hypothesis proposes happened to Venus. The planet was spinning prograde, the normal direction, the same direction everything else was going. Then something enormous struck it from the right angle, transferred enough reverse angular momentum, and flipped its effective rotation. This idea had a powerful precedent. Earth itself appears to have experienced exactly this kind of event. Around 4.5 billion years ago, a Mars-sized body that scientists have named Theia struck the young Earth. The collision was catastrophic. It liquefied much of Earth's surface, ejected a vast cloud of debris into orbit, and from that debris, the Moon coalesced. The Theia impact didn't just give us the Moon. It set Earth's axial tilt at roughly 23.5 degrees, the tilt responsible for our seasons. It may have contributed to Earth's relatively fast initial rotation. It fundamentally shaped our planet's identity. The evidence for Theia is worth lingering on, because it shows us what a giant impact actually leaves behind. When scientists first proposed that the Moon formed from a collision with Earth, it was a bold claim. But then, the Apollo missions brought lunar rocks home, and those rocks told a very specific chemical story. The oxygen isotope ratios in Moon samples match Earth's almost exactly, far too closely to be coincidence. Yet the Moon is depleted in iron and volatile elements in ways that make perfect sense if it condensed from a ring of superheated debris blasted off Earth's outer layers. The impact did not just knock something loose, it reshaped the chemistry of an entire system. The timeline matters too. Isotopic dating places the Moon-forming impact at roughly 60 to 100 million years after the solar system's birth, right in the middle of that late accretion chaos, right when we would expect the largest surviving embryos to be sweeping up the last of their neighbors. Theia was probably comparable in mass to Mars, and it struck Earth at an angle and speed that happened to produce a large, lasting moon. But tilt the angle slightly, increase the speed, change the mass ratio, and the outcome could have been profoundly different. Perhaps no moon at all, perhaps a world spinning in the opposite direction. So if one giant impact could explain Earth's tilt, Earth's moon, and Earth's rotation rate, why couldn't another giant impact explain Venus's backward spin? The logic felt clean. The early solar system was violent. Giant impacts were not rare events, but expected outcomes of planetary formation. Computer simulations of the late accretion phase consistently produce scenarios where Mars-sized embryos collide with growing planets. It would have been more surprising if Venus had avoided such an encounter entirely. And the impact hypothesis had another appeal. It was narratively satisfying. It gave Venus's strangeness a single, identifiable cause. A moment, a before and after. Venus was normal, and then something hit it, and then it wasn't. Scientists like identifiable causes. We all do. When something is wrong, we want to point at the thing that made it wrong. The giant impact hypothesis let us do that. It said Venus's backward rotation is a scar, evidence of a specific event that happened at a specific time billions of years ago. There is something deeply human about wanting a cause you can point to, a moment you can circle on a timeline and say, here, this is when everything changed. The impact hypothesis offers exactly that, and in science, where so many explanations involve slow accumulations and statistical tendencies, a single dramatic event carries a special kind of persuasive power. It feels like a story with a beginning and an end. A planet was spinning one way, something struck it, and afterward it was spinning another way, clean, decisive, almost cinematic. And this preference for identifiable causes is not a flaw in scientific thinking, but it is a bias worth noticing. We are pattern-seeking creatures who find comfort in narratives that have clear turning points. The impact hypothesis satisfies that instinct beautifully, perhaps too beautifully, because the universe is under no obligation to organize itself into stories that feel satisfying to human minds. Sometimes the answer to why, is not a single event, but a long, tangled chain of ordinary processes, none of them dramatic on their own, all of them necessary in combination. For decades, this was the leading explanation, not proven certainly, but accepted as the most plausible candidate. Textbooks mentioned it, documentaries depicted it. When people asked why Venus spins backward, this was the answer most often given. A giant impact, a cosmic collision, a world knocked sideways, or rather, knocked backward. It is a compelling story. And like many compelling stories, it begins to unravel when you look at it more carefully. The giant impact hypothesis is satisfying, but satisfaction is not the same as evidence. And when planetary scientists began running the numbers more carefully, problems emerged. The first problem is energy. To flip Venus's rotation from prograde to retrograde, you need to first cancel out all of its original angular momentum, bring it to a dead stop, and then spin it back up in the opposite direction. That requires an extraordinary amount of energy delivered in a very specific way. The impactor would need to be massive. Simulations suggest something in the range of 1 to 3 times the mass of Mars. But mass alone is not sufficient. The geometry of the impact matters enormously. A head-on collision would shatter both bodies and produce something unrecognizable. The impact needs to be oblique, a glancing blow that transfers angular momentum efficiently without completely destroying the target. That's a narrow window. Too direct, and you get catastrophic disruption. Too glancing, and the impactor skims past without transferring enough momentum. The angle, the speed, and the mass all have to fall within a surprisingly tight range. This is not impossible, of course. Unlikely events do happen. The Theia impact on Earth required its own set of specific conditions, and it clearly occurred. But the tightness of the parameter window is worth noting. It means we are not describing something that would happen easily or often. The second problem is more striking. Where is the Moon? When Theia struck Earth, the collision produced an enormous disk of debris orbiting the planet. That debris disk coalesced into the Moon within perhaps a few thousand years. The Moon is, in a very real sense, the receipt for Earth's giant impact. It is the physical evidence that the collision occurred. Venus has no moon. None at all. It is one of only 2 planets in the inner solar system without one. The other being Mercury, which is so small and so close to the Sun that retaining a moon would be gravitationally difficult regardless. But Venus is not small. Venus is nearly the size of Earth. If it experienced a giant impact comparable to the one that gave Earth its moon, where is the debris? Where is the moon that should have formed? In 2006, 2 researchers at Caltech, Ali Alemi and David Stevenson, tackled this question directly. Their work remains one of the most careful analyses of the Venus impact scenario. Alemi and Stevenson showed that a giant impact on Venus could, under certain conditions, produce a moon. But that moon would have a problem. Venus sits closer to the Sun than Earth does, and this matters because every planet has a gravitational boundary called the Hill sphere. The Hill sphere is the region within which the planet's gravity dominates over the Sun's. Venus's Hill sphere is smaller than Earth's because Venus is closer to the Sun, and the Sun's gravitational influence is correspondingly stronger. A moon formed from impact debris around Venus would need to orbit within this smaller sphere to survive. But here is the difficulty. Tidal interactions between Venus and any moon would cause that moon's orbit to evolve over time. Depending on the relative spin rates, tidal forces could push the moon outward, eventually beyond the Hill sphere, where the Sun would strip it away, or tidal forces could pull the moon inward, sending it spiraling down to crash back into Venus. Alemi and Stevenson found that either outcome was plausible. A Venus-born moon might simply not survive. It would either escape or be reabsorbed, leaving no trace. This is clever, and it technically rescues the impact hypothesis from the missing moon objection. But notice what it does to the argument. The impact hypothesis originally gained appeal because it was simple and explanatory. Now it requires an additional step. Not only did a giant impact happen, but a moon also formed and then was subsequently destroyed by tidal evolution. the explanation has become more complicated. It has acquired a secondary hypothesis to patch the first. The third problem is the surface itself. If a giant impact occurred, it would have left signatures in Venus's geology, impact basins, compositional anomalies, structural asymmetries in the crust. On Earth, we can trace evidence of the Theia impact in the chemistry of lunar samples, in the isotopic ratios of certain elements, in the structure of Earth's mantle. On Venus, that evidence is gone. Venus resurfaces itself. The entire planet appears to have undergone a global volcanic resurfacing event, or series of events, that replaced most or all of its crust roughly 300 to 700 million years ago. The average surface age of Venus is younger than many features on Earth's continents. Whatever happened to Venus 4 billion years ago, the physical record has been paved over. This doesn't disprove the impact hypothesis, but it means the hypothesis cannot be confirmed through surface geology. The evidence that might settle the question has been destroyed. So where does this leave us? The giant impact hypothesis is not impossible. Nothing in physics prevents it. But it requires a narrow set of initial conditions. It fails to explain the absence of a moon without invoking additional mechanisms, and it cannot be tested against the geological record. It is an explanation that could be true, but could be true is a low bar in science. We need to look further. In 2008, a different version of the story emerged. Not a collision between a planet and a stray impactor, but a merger between two bodies that were both destined to become Venus. To understand this idea, you need to appreciate something about how the final stages of planet formation work. The inner solar system did not go from dust to 4 neat planets in a smooth progression. The late stage of accretion was messy. Simulations consistently show that the last phase involved a relatively small number of large planetary embryos, perhaps a dozen or so, each roughly the mass of Mars or larger, occupying overlapping or neighboring orbits. These embryos interacted gravitationally. They perturbed each other's orbits, and eventually, over tens of millions of years, they collided and merged, 2 by 2, until the 4 terrestrial planets we know today had assembled. The late accretion phase was a time of gravitational restlessness. As the number of planetary embryos dwindled, the survivors grew larger, and larger bodies exert stronger gravitational influence on everything around them. Jupiter and Saturn, already massive by this point, acted as distant orchestrators, their gravity tugging on the orbits of inner embryos in subtle but accumulating ways. Over millions of years, those tugs could stretch a nearly circular orbit into something more elliptical, more likely to intersect with a neighbor's path. The last giant mergers in the inner solar system were not random in the sense of being unpredictable from first principles. They were random in the sense that the outcomes depended on initial conditions so precise, so sensitive to tiny variations, that no amount of information could have forecast them. The timescales involved are humbling. The final assembly of the terrestrial planets probably stretched across 50 to 100 million years. That is a long time by any human measure, but it is brief by planetary standards. Brief enough that the last major merger for Venus could have happened while Earth was still settling from its own. 2 neighboring worlds, each undergoing their final, defining collisions within a few tens of millions of years of each other, each emerging with completely different rotational states. Not because the physics was different, but because the geometry of each final encounter was unique. The merger hypothesis proposes that Venus was the product of one of these final mergers. 2 bodies of comparable size, each perhaps half the mass of present-day Venus, combined in a collision that happened to produce a net retrograde spin. How would a merger produce retrograde rotation? It depends on the geometry. If the two bodies approach each other on slightly offset trajectories, the angular momentum of their mutual orbit gets converted into the spin of the merged body. Depending on the angle and direction of approach, that spin could end up in either direction, prograde or retrograde. It is, in a meaningful sense, a coin flip. This is where the work of Seth Jacobson and colleagues becomes relevant. In a series of studies, Jacobson and collaborators ran large numbers of accretion simulations, tracking not just the final masses and orbits of the resulting planets, but also their spins. What they found was striking. The final spin states of terrestrial planets in these simulations were essentially random. There was no strong preference for prograde rotation. Some planets ended up spinning forward. Some ended up spinning backward. Some ended up barely spinning at all. The direction and rate of rotation depended sensitively on the details of the last one or two major collisions, and those details varied chaotically from simulation to simulation. This result reframes the entire question. If the final spins of terrestrial planets are naturally random, then Venus spinning retrograde may not require any special explanation at all. It might simply be the outcome Venus happened to get. The same way a coin landing tails doesn't require a theory about why tails came up. It just did. Consider what it would mean to take the coin flip seriously as a statistical claim. If each terrestrial planet's final spin direction were truly random, a 50-50 chance of prograde or retrograde, then having 1 out of 4 planets end up retrograde is not surprising at all. It is, in fact, the single most probable outcome for a group of 4. The probability of getting exactly 1 retrograde spinner out of 4 independent coin flips is about 25%. Getting 0 retrograde planets would be less likely, at just over 6%. The math does not demand an explanation for Venus. If anything, the math would demand an explanation if all 4 planets happen to spin the same way. But we resist this reasoning, and for understandable reasons. A coin flip feels like a non-answer. It feels like the scientist shrugging and saying, "It just happened that way." We want mechanisms, not statistics. We want to know what the coin is made of, who flipped it, how high it went. And this discomfort with randomness as an explanation reveals something about the boundary between physics and narrative. Physics is perfectly comfortable with probabilistic outcomes. A radioactive atom decays or it does not, and no deeper cause determines which. But when we look at something as large and singular as a planet spinning backward, probability feels too thin, too weightless to hold the explanatory burden we want to place on it. The merger hypothesis, in this framing, is less a specific mechanism and more a statistical argument. Venus's spin is unusual compared to the other planets we observe, but we only observe 4 terrestrial planets. That is a very small sample. Drawing conclusions about what is normal from a sample of 4 is statistically fragile. There is an elegance to this. The merger hypothesis does not require fine-tuned parameters. It does not need a specific impact to mass or a specific angle. It simply says that the chaotic nature of late-stage accretion produces a range of outcomes, and Venus landed on one end of that range. That elegance deserves a moment of appreciation, because it is a rare quality in planetary science. Most hypotheses for Venus's retrograde rotation require you to add something to the story. A giant impactor that arrived at just the right angle, a thick atmosphere that interacted with solar tides over billions of years, a captured satellite that slowly drained the planet's spin. Each of these is an additional ingredient, an extra assumption layered on top of what we already know about planet formation. The merger hypothesis asks for nothing extra. It simply points to a process we already believe occurred and says the outcome you see is one of the ordinary possibilities. There is a deep scientific principle at work here, sometimes called parsimony, sometimes called Occam's razor. When two explanations account for the same observations, prefer the one that requires fewer assumptions. The merger hypothesis may not give us a vivid story, but it gives us something arguably more valuable. An explanation that does not need to be explained itself, but there is also a limitation, and it is a fundamental one. The merger hypothesis is essentially untestable. We cannot rewind the solar system and watch Venus form. We cannot observe the specific collision or merger that set its spin. We have no debris, no moon, no isotopic signature that we can currently access to distinguish between a merger and a single body formation, followed by a later impact. Venus's resurfaced geology offers no help. The merger hypothesis is consistent with physics. It is consistent with simulations. It is plausible. But it makes no unique predictions that we could verify or falsify with current technology. And so, science does what science does when a question resists direct observation. It looks for mechanisms that operate on timescales we can model, through physics we can test, with predictions we can check, which brings us to a very different kind of explanation, one that does not require any collision at all. What if nothing hit Venus? What if Venus was never struck by a giant impactor, never formed from a dramatic merger, never experienced any single catastrophic event that reversed its rotation? What if Venus simply slowed down? In 2001, two French celestial mechanicians, Alexandre Correa and Jacques Lascar, published a paper that reframed the entire question. They showed that Venus's retrograde rotation could be explained not by a sudden event, but by the patient, cumulative action of physical forces operating over billions of years. No impact required, no collision, just torques. 3 of them, each pulling Venus's rotation in a different direction, each operating on a different timescale, all of them fighting one another for 4.5 billion years. To understand this, you need to understand what a torque is in this context. A torque is simply a twisting force. When you turn a wrench, you are applying a torque. When you push a merry-go-round, you are applying a torque. A torque does not move something in a straight line. It rotates it. Venus is subject to 3 distinct torques, each caused by a different physical mechanism, and their interplay is the key to everything. The first torque is the solar gravitational tide. This is the same kind of force that causes ocean tides on Earth, but operating on the solid body of the planet itself. The Sun's gravity is not uniform across Venus. The side of Venus facing the Sun is pulled slightly more strongly than the far side. This differential pull creates a tidal bulge, a subtle elongation of the planet's shape along the Sun-Venus line. Now, if Venus is rotating, that tidal bulge does not point perfectly at the Sun. It gets carried slightly ahead of the Sun-Venus line by the planet's rotation, the same way Earth's ocean tidal bulge is carried slightly ahead of the Moon by Earth's rotation. The Sun's gravity then pulls on that displaced bulge, and because the bulge is offset from the direct Sun-Venus line, the pull creates a torque. Specifically, it creates a torque that opposes the rotation. It acts as a brake. Think of it this way. Imagine you are on a merry-go-round that is spinning, and someone reaches out and grabs the edge, but not quite at the right moment. They grab slightly behind where they were aiming, and the result is that their grip creates a drag, a force that resists the spinning. That is what the solar gravitational tide does to Venus. It tries to slow the planet's rotation down, and over billions of years, that braking effect accumulates. But this torque alone would not reverse Venus's rotation. It would slow Venus to a stop, and then the planet would settle into a state called synchronous rotation, where the same face always points at the sun, the way the moon always shows the same face to Earth. If only the gravitational tide were acting, Venus would be tidally locked to the sun. Venus is not tidally locked. Something else is intervening. This is the torque that makes Venus's story unique in the solar system. And it requires some patience to understand, because it is genuinely strange. Venus has an atmosphere that is almost 100 times more massive than Earth's, 92 bars of pressure at the surface, mostly carbon dioxide. This atmosphere absorbs an enormous amount of solar energy, particularly in the upper cloud layers around 60 to 70 kilometers altitude. When sunlight heats the dayside atmosphere, it does something you might not expect. It creates a pressure bulge. The heated atmosphere expands slightly. The atmospheric mass redistributes. More mass accumulates on the dayside, creating a region of slightly higher pressure. Now, remember what happened with the gravitational tidal bulge. It got carried ahead of the Sun-Venus line by the planet's rotation, and that offset allowed the sun to pull on it and create a braking torque. The atmospheric thermal bulge does the same thing, but in reverse. Here is why. The atmosphere takes time to respond to heating. The sun beats down on a patch of atmosphere, but the maximum pressure does not build up instantly. There is a lag. By the time the atmosphere reaches its maximum response, Venus's rotation has carried that patch slightly past the point directly facing the sun. Because the thermal bulge is offset in the direction of rotation rather than behind it, the sun's gravitational pull on this atmospheric mass creates a torque that pushes Venus's rotation forward, not backward. It accelerates the rotation rather than braking it. This is remarkable. The atmosphere of Venus is acting as an engine. Solar energy comes in, heats the atmosphere, creates a pressure asymmetry, and that asymmetry gets converted into a torque that drives the planet's rotation. Let me try an analogy. Imagine you are sitting on a playground roundabout, the flat spinning platform kind. Someone is pressing a brake pad against the edge, slowing you down. That is the gravitational tide. But at the same time, a steady wind is blowing against a sail you have mounted on the roundabout, pushing it forward. That is the atmospheric thermal tide. The brake wants to stop you. The sail wants to keep you going. What actually happens depends on which one is stronger. On Earth, this effect is negligible. Our atmosphere is too thin. The thermal tide exists, but it is overwhelmed by other factors. On Venus, with its massive atmosphere, the thermal tide is a major player. It can compete directly with the gravitational tide. The third torque is quieter. Venus, like Earth, almost certainly has a liquid outer core. That liquid core does not have to rotate at exactly the same rate as the solid mantle above it. There can be a slight mismatch, and where there is a mismatch between a liquid layer and a solid layer, there is friction at the boundary. This friction acts as another brake, but a weak one. It slowly nudges the core and mantle toward the same rotation rate. Over billions of years, this gentle coupling helps dissipate energy and can influence where the system settles. Think of it as a third hand on the merry-go-round, not pushing, not pulling the brake, just resting lightly against the surface, adding a small drag that accumulates over deep time. Now here is where Correa and Laska's genius lies. They showed that the relative strengths of these three torques depend on how fast Venus is spinning. When Venus was young and spinning faster, the gravitational tide dominated. It was the strongest brake. It slowed Venus down steadily over hundreds of millions of years. The atmospheric thermal tide existed, but at high rotation rates, it was weaker than the gravitational braking. But as Venus slowed, something changed. The gravitational tide weakened. This is because the braking torque depends on how fast the bulge is offset from the Sun-Venus line, and that offset depends on rotation rate. Slower rotation means less offset, means less torque. Meanwhile, the thermal tide did not weaken as quickly. As Venus approached very slow rotation rates, the thermal tide became competitive, and then it became dominant. Correa and Lasker showed that there is a range of very slow rotation rates where the thermal tide actually overpowers the gravitational tide. In this regime, instead of Venus settling into tidal lock, the atmospheric engine keeps pushing. Venus's rotation continues to slow, passes through zero, and begins increasing in the retrograde direction. The planet's rotation declined through zero and reversed, not because something struck it, because the physics of tides, atmospheres, and friction naturally guided it to this state. Correa and Lasker published refinements of this model in 2003, exploring how different assumptions about Venus's core viscosity, atmospheric density, and initial rotation rate affected the outcome. What they found was that for a wide range of plausible starting conditions, Venus naturally evolves to a state very close to what we observe today. Slow retrograde rotation, a 243-day period, consistent with the measured values. Think about what billions of years actually means for these forces. A human lifetime is roughly 80 years. 1,000 human lifetimes, placed end to end, gets you to 80,000 years, which is less than the time since the last glacial maximum on Earth. 1 million human lifetimes gets you to 80 million years, which is roughly when a large asteroid ended the reign of the dinosaurs. The forces that Correa and Lasker describe have been operating for more than 50 times that span. 50 Cretaceous extinctions laid end to end, and the talkers have been pushing the whole time. Every single day, every single year, every single geological epoch. The same three forces leaning on the same spinning world. The work is invisible on any timescale a human being can experience. You could watch Venus for 10,000 years and measure no change in its rotation rate. But the change is there, accumulating in increments too small for any instrument to detect in real time, adding up across eons the way grains of sand add up into dunes. And the merry-go-round analogy from earlier deserves another moment. Imagine that merry-go-round in a park, and imagine someone has attached a small sail to its frame. The wind pushes on the sail, and friction from the axle resists the spin. And the ground rumbles faintly beneath the platform, transmitting its own subtle drag. Three forces, all acting at once, all different in strength and direction. On any given afternoon, the merry-go-round barely moves. But leave it for a century, for a millennium, for 1 billion years, and the cumulative effect of those three forces will determine, with absolute certainty, which way it turns and how fast. The sail does not need to be large. The friction does not need to be strong. They only need to be persistent. What makes the Correa-Lasker result robust, in the technical sense, is that it does not depend on precise values. The model works across a wide range of atmospheric densities, a wide range of core mantle friction strengths, a wide range of starting conditions. Venus does not need to have begun with exactly the right spin rate, or exactly the right atmospheric mass, or exactly the right internal structure. The three-torque system is what mathematicians call an attractor. It pulls a broad family of initial conditions toward the same final state. This is the opposite of fine-tuning. Fine-tuning would mean that only one very specific set of starting parameters produces retrograde rotation. The Correa-Lasker model says that a whole neighborhood of starting parameters will get you there. The destination is the same, only the journey varies. This was not a fine-tuned result. It was robust. It did not require a specific impactor mass or a specific collision angle. It required only that Venus have a thick atmosphere and be close enough to the Sun for tidal forces to matter, both of which are simply true. The slow physics hypothesis does not give you a dramatic moment. There is no collision, no explosion, no single event you could point to and say, that is when Venus changed. Instead, it gives you something quieter and, in its own way, more profound. A planet being gradually reshaped by the cumulative whisper of forces too subtle to notice on any human timescale, but relentless over billions of years. Venus was not knocked backward, it was guided there. To truly appreciate what the thermal tide is doing, you need to understand the atmosphere doing it. And Venus's atmosphere is something unlike anything else in the solar system. At the surface of Venus, the atmospheric pressure is approximately 92 bars. That is 92 times the pressure at sea level on Earth. It is roughly equivalent to the pressure you would experience at a depth of 900 meters beneath the ocean's surface on our planet. Nearly a kilometer of water pressing down on you from above. The atmosphere is composed almost entirely of carbon dioxide, about 96.5%. The remainder is mostly nitrogen, with traces of sulfur dioxide and other compounds. This blanket of CO2 produces a greenhouse effect of staggering magnitude. Venus's surface temperature averages around 465 degrees Celsius, roughly 870 degrees Fahrenheit, hotter than Mercury, despite being nearly twice as far from the Sun. But the heat and pressure, as extreme as they are not the strangest part. The strangest part is the wind. Venus's solid surface takes 243 Earth days to complete one rotation. But the upper atmosphere, at the cloud top level around 65 to 70 kilometers altitude, circles the entire planet in just 4 days. The cloud top winds reach speeds of roughly 100 meters per second. That is 360 kilometers per hour, faster than many hurricanes on Earth. This phenomenon is called atmospheric superrotation, and it is one of the most persistent mysteries in planetary science. On Earth, our atmosphere generally moves at speeds comparable to or slower than the planet's surface rotation. Wind speeds rarely exceed a small fraction of the rotational velocity. The atmosphere is dragged along by friction with the surface, and while weather systems create local variations, the bulk atmosphere is coupled to the solid planet beneath it. The mystery runs deep. On Earth, atmospheric winds are fundamentally a consequence of planetary rotation. The faster the planet spins, the stronger the Coriolis deflection, and the more organized the wind patterns become. Venus, by this logic, should have almost no organized atmospheric circulation at all. A planet rotating once every 243 days generates negligible Coriolis force. The atmosphere should slosh around lazily, driven by local temperature differences, with no global structure to speak of. Instead, the entire atmospheric envelope is organized into a single, coherent, planet-encircling flow that has maintained itself for as long as we have been able to observe it. We can describe what is happening. We struggle to explain why. General circulation models, the same kinds of computer simulations used to study Earth's weather and climate, have been adapted for Venus. Some of them can reproduce superrotation under certain conditions, but the results are sensitive to assumptions about how momentum is transferred vertically through the atmosphere, how waves interact with the mean flow, and how surface topography couples to the winds above. Different models, using slightly different assumptions, produce different results. The superrotation is reproducible, but not yet predictable from first principles. It hovers at the edge of our understanding, close enough to tantalize, far enough to humble. On Venus, that coupling is inverted. The atmosphere is not following the surface. It is outrunning it by a factor of 60. The tail is wagging the dog. The Japanese space agency JAXA's Akatsuki orbiter, which arrived at Venus in 2015 after a dramatic orbital insertion recovery, has provided the most detailed observations of this superrotation to date. Akatsuki carries cameras that image Venus at multiple wavelengths, from ultraviolet through near-infrared, revealing different layers of the atmosphere simultaneously. What Akatsuki revealed is that the superrotation is not a simple, uniform conveyor belt. There are waves, vortices, and thermal structures embedded within the flow. Enormous bow-shaped features, standing atmospheric waves anchored to mountain ridges on the surface below, stretch across thousands of kilometers. The polar vortices, one at each pole, are complex, sometimes appearing as double-eyed structures that shift and evolve over days. Akatsuki has revealed details that ground-based telescopes could never resolve. The bow-shaped wave that stretches across the cloud tops, anchored to the mountainous terrain of Aphrodite Terra far below, was one of its most striking discoveries. This stationary gravity wave, nearly 10,000 kilometers long, demonstrated that Venus's surface topography can reach up through 65 kilometers of dense atmosphere and leave its fingerprint on the cloud deck. The solid planet and its gaseous envelope are more tightly linked than anyone had assumed. Akatsuki also captured detailed images of the polar vortices, enormous rotating storm systems at both poles where the atmospheric flow converges and descends. These vortices are not fixed structures. They shift, split, and reform over days and weeks, suggesting a level of atmospheric variability that complicates any simple picture of Venus's wind patterns. The atmosphere of Venus is alive in a way that few people appreciate. Far from a static blanket, it is a dynamic, churning, self-sustaining system that contains more mass than Earth's entire atmosphere by nearly 2 orders of magnitude. And this brings us back to the thermal tide and why it matters so much for Venus's rotation. The scientists who first identified this atmospheric coupling were Thomas Gold and Soter in 1969. They recognized that Venus's thick atmosphere could transfer angular momentum to and from the solid planet, and that this transfer could affect the planet's rotation over geological time. Gold and Soter's insight was simple but profound. The atmosphere is not separate from the planet. It is physically coupled to it. Friction at the surface, pressure against mountain ranges, gravitational interaction between the atmospheric mass distribution and the solid body below. All of these mechanisms transfer angular momentum between the atmosphere and the surface. If the atmosphere gains angular momentum from an external source, in this case solar heating creating the thermal tidal bulge, it can transmit that angular momentum to the solid planet. The atmosphere acts as an intermediary. Solar energy enters, gets converted into atmospheric motion, and that motion gets coupled to the planet's rotation through surface friction and gravitational torques. In 1978, Andrew Ingersoll and Anthony Dobrovolsky's at Caltech built on Gold and Soter's work with a more rigorous mathematical treatment. They calculated the magnitude of the atmospheric thermal tide on Venus and showed that it was large enough to compete with the gravitational tide. This was not obvious beforehand. Many researchers had assumed that atmospheric effects would be negligible compared to solid body tidal forces. Ingersoll and Dobrovolsky's demonstrated otherwise. On Venus, With its thick atmosphere and slow rotation, the atmospheric thermal tide is a major force, perhaps the dominant force determining the planet's present-day spin state. Consider the scale of what this means. Venus's atmosphere, which represents less than 1/100th of 1% of the planet's total mass, is controlling the rotation of the entire solid body beneath it. 92 bars of gas draped over a world of rock and iron, and that gas is the dominant factor determining how fast the rock and iron spin. This is possible because of leverage. The atmosphere sits at the surface, at the maximum possible distance from the planet's center of mass. Angular momentum depends not just on mass, but on how far that mass is from the axis of rotation. The atmosphere, spread across the entire outer surface of the planet, has enormous leverage despite its relatively small mass. And the sun provides a constant, reliable energy source. Every moment of every day, for billions of years, solar radiation has been pouring into Venus's dayside atmosphere, maintaining the thermal pressure bulge, maintaining the torque, maintaining the slow, persistent push. The atmosphere is not just a passive layer of gas sitting on top of a planet. It is a physical engine. It absorbs energy from an external source, converts that energy into mechanical force, and applies that force to the solid body it surrounds. It is a heat engine in the thermodynamic sense, with the sun as the hot reservoir and the deep space of Venus's night side as the cold reservoir, and the work output is a torque on the planet's rotation. This is what makes the slow physics hypothesis so compelling. It does not require a lucky accident. It does not require a specific impactor arriving at a specific angle at a specific time. It requires only the ingredients that Venus already has: a thick atmosphere, a nearby star, and time. The atmosphere does the rest. 4.5 billion years of patient, invisible physics. No drama, no collision, just the quiet, persistent work of sunlight, gas, and gravity, reshaping a world one infinitesimal push at a time. And Venus's atmosphere, that crushing, opaque, superheated envelope that makes the planet so hostile to everything we know about life, turns out to be the very thing that made Venus what it is. Not an obstacle to understanding, the key to it. There is a problem with Venus that has nothing to do with the physics. The physics, as we've seen, offers several plausible stories. The problem is that more than one of those stories ends in exactly the same place. Imagine two detectives arriving at a crime scene. One concludes the window was broken from the outside. The other concludes it was broken from the inside, and then someone carefully rearranged the glass. Both accounts explain every shard on the floor. Both predict the same fingerprint patterns, and there is no surveillance footage. This is roughly the situation planetary scientists find themselves in with Venus's spin. The first path is the one we spent time with earlier. Solar gravitational tides, possibly aided by tides in a thick early atmosphere, slowly drain the planet's angular momentum. Venus decelerates. It passes through a state of near-zero rotation. And then, nudged by the asymmetric pull of the sun on its dense atmosphere, it begins turning the other way, slowly, retrograde. This is a process that takes billions of years. It is gentle, it is patient, and at the end, you get a planet rotating once every 243 Earth days, backward. The second path is more dramatic but leads to the same quiet outcome. Instead of the spin slowing and reversing, the entire axis of the planet tilts. Venus flips over. If you tip a spinning top past 90 degrees, it now appears to spin the other way, even though the rotation itself never changed direction. It just changed orientation. A planet with an axial tilt of 177 degrees, which is what Venus has, is almost upside down. And an upside down planet spinning prograde looks, from the outside, exactly like a right-side-up planet spinning retrograde. Both paths arrive at the same observable state, the same spin rate, the same axial tilt, the same relationship between the planet and the Sun. In 2003, Alexandre Correa and Jacques Lascar, working with Olivier de Surgy, published a study that laid this problem out with uncomfortable clarity. They modeled the long-term spin evolution of Venus under a range of initial conditions, different starting spin rates, different atmospheric densities, different tidal parameters, and they found that many of those initial conditions converged on the same final state. This convergence is a feature of the dynamics, not an accident. The tidal forces acting on Venus are dissipative, meaning they remove energy from the system over time. And dissipative systems tend to forget their initial conditions. They settle into attractors, stable endpoints that the system flows toward regardless of where it started. Think of it like water running down a mountainside. It doesn't matter whether the rain fell on the north slope or the south slope. If both sides drain into the same valley, you'll find the water in the same river at the bottom. And looking at the river tells you nothing about which slope the rain fell on. In the language of mathematics, this is called observational degeneracy. Two or more histories produce identical observables. The present-day measurement cannot distinguish between them. This is not a failure of our instruments. Better telescopes will not resolve it. More precise measurements of Venus's current spin rate will not help, because both paths predict the same spin rate. The degeneracy is structural. It lives in the equations themselves. Now, there are subtle differences between the two scenarios that might, in principle, leave traces. A giant impact that flipped the axis would have deposited enormous energy into the planet's interior, potentially affecting its geological history. A gradual tidal spin down would have subjected the surface to changing day-night cycles over billions of years, which could influence atmospheric evolution in particular ways. But Venus, as we are about to see, has been remarkably thorough in erasing its own past. The traces that might have distinguished these histories have been overwritten. The geological record that might have preserved a signature of impact heating versus tidal deceleration has been resurfaced. The atmospheric chemistry that might have recorded different thermal histories has been processed and reprocessed by billions of years of volcanic outgassing. So we are left with a planet that we can observe in extraordinary detail, whose present state we can measure with great precision, and whose past we cannot uniquely reconstruct from those measurements alone. This is a humbling result. We are accustomed to the idea that if we just look carefully enough, the evidence will tell us what happened. In most of science, that faith is justified. But planetary spin evolution is one of those domains where the evidence, no matter how carefully examined, may genuinely underdetermine the history. And yet, the fact that we can identify and name this degeneracy is itself a kind of progress. Knowing precisely what we cannot know is not the same as knowing nothing. It tells us where to look for the rare clues that might break the symmetry between these two histories. It tells us what kinds of measurements would be diagnostic, even if those measurements are difficult or currently impossible. Correa and Lascar's work did not solve the mystery of Venus's rotation. It did something arguably more important. It defined the shape of the mystery. It told us that the question, "Why does Venus spin backward?" may not have a unique answer recoverable from observation. And that understanding, uncomfortable as it is a genuine piece of knowledge about the universe. If you wanted to solve the puzzle of Venus's spin, you would want to read the planet's geological record. You would want ancient rocks, old craters, magnetic signatures frozen in cooled lava. the kinds of evidence that on Earth let us reconstruct billions of years of history, you would want a planet that kept good records. Venus did not keep good records. In 1990, NASA's Magellan spacecraft entered orbit around Venus and began mapping the planet's surface with synthetic aperture radar. Radar was necessary because Venus's atmosphere is opaque to visible light. You cannot photograph Venus's surface from orbit, but radar penetrates the clouds, bounces off the terrain, and returns a signal that can be assembled into detailed images. Over the next 4 years, Magellan mapped 98% of Venus's surface at a resolution of about 100 meters. It was and remains one of the most complete planetary mapping campaigns ever conducted. What Magellan revealed was a world dominated by volcanism. Vast lava plains covering most of the surface, shield volcanoes, lava channels thousands of kilometers long, pancake-shaped volcanic domes unlike anything on Earth, and everywhere, the signatures of a planet shaped primarily by heat rising from below. But the most striking finding was not what was on the surface, it was what was missing. Venus has roughly 1,000 impact craters. That number in itself is not unusual. What is unusual is their distribution. On most planetary bodies, craters accumulate over time, so older surfaces have more craters and younger surfaces have fewer. You can read the age of a surface by counting its craters. This technique, called crater counting, is one of the fundamental tools of planetary geology. On Venus, the craters are spread almost randomly across the entire surface. There are no heavily cratered ancient highlands. There are no crater-free young volcanic regions. The crater population looks as though someone wiped the surface clean and then started the clock fresh everywhere, all at once. The implications were startling. The simplest interpretation is that Venus's entire surface is roughly the same age. Estimates based on the crater density place that age somewhere between 300 and 700 million years. This means that something happened, roughly 500 million years ago, that erased the previous surface and replaced it with the one we see today. The leading hypothesis is global volcanic resurfacing, a catastrophic episode or perhaps a sustained period of volcanic activity covered the planet in fresh lava, burying the older crust beneath kilometers of new basalt. Every crater that had accumulated over the preceding 4 billion years was filled in or covered over. Every geological structure was entombed. This resurfacing event, if it happened as a single catastrophic episode, would have been one of the most dramatic geological events in the solar system's history. An entire planet remade. Some researchers have proposed instead that the resurfacing was more gradual, a sustained period of high volcanic activity lasting hundreds of millions of years that collectively replaced the surface. The crater statistics can accommodate either interpretation, though the uniform distribution tends to favor a relatively sudden event. For our purposes, what matters is this: whatever geological record Venus once had, the record that might have told us about its early spin state, about impacts that might have altered its rotation, about tidal interactions preserved in ancient rock formations, that record is buried, perhaps permanently. There is no magnetic field to consult either. Earth's magnetic field is generated by convection in its liquid iron core, and ancient magnetic orientations are preserved in rocks as they cool, creating a magnetic record that stretches back billions of years. This paleomagnetic record has been essential for understanding Earth's geological and rotational history. Venus has no global magnetic field. Whether it ever had one is unknown, and without a magnetic field, there is no magnetic record frozen in the rocks, even in the rocks that survived the resurfacing. This is another archive that simply does not exist. so the geological record is gone. The magnetic record never existed, or at least was never preserved. Is there anything left? There is one surviving clue, and it lives not in the rocks, but in the atmosphere. It is the ratio of deuterium to hydrogen in Venus's water vapor. Deuterium is heavy hydrogen. A hydrogen atom with an extra neutron. In any body of water, a small fraction of the hydrogen atoms are deuterium. On Earth, the ratio of deuterium to ordinary hydrogen, called the DH ratio, is about 1.6 parts per 10,000. This ratio reflects the conditions under which Earth's water was delivered and the processes that have affected it since. On Venus, the DH ratio is approximately 150 times Earth's value. This measurement was first made by the Pioneer Venus mission in 1978, and it has been refined by subsequent observations. The enrichment is enormous, and it tells a story. When water molecules in an atmosphere are broken apart by ultraviolet light, the lighter hydrogen atoms escape to space more easily than the heavier deuterium atoms. Over time, this preferential escape enriches the remaining water in deuterium. The more water you lose, the higher the DH ratio climbs. A DH ratio 150 times Earth's value suggests that Venus once had vastly more water than it does today, possibly enough to constitute a shallow ocean. In 2016, Michael Way and colleagues at NASA's Goddard Institute for Space Studies published climate models suggesting that Venus could have maintained habitable surface conditions, including liquid water, for as long as 2 billion years. Their models showed that even with the higher solar flux Venus receives, a slowly rotating planet with a modest ocean could develop a thick dayside cloud deck that reflected enough sunlight to keep temperatures moderate. A slowly rotating Venus, that detail matters. The habitability models depend on Venus's rotation rate because the day-night cycle controls cloud formation and heat distribution. If Venus was spinning faster in the past, the climate dynamics would have been different. The DH ratio tells us water was lost, but it cannot tell us how fast Venus was spinning when that water was present. The DH ratio is a chemical fossil. It is perhaps the only surviving quantitative clue to Venus's ancient surface conditions. But like all fossils, it is incomplete. It records the fact of water loss without recording the full context in which that loss occurred. Venus resurfaced itself. It lost its magnetic record. It baked away its oceans. And in doing so, it destroyed nearly every piece of evidence that might have told us how it came to spin the way it does. What remains is a planet whose present state is exquisitely measured and whose past is almost entirely opaque. We are not done asking Venus questions. After decades of relative neglect, 3 major missions are now being prepared to return to Venus, and each one is designed to address a different piece of the planet's story. The first is Da Vinci. Da Vinci is a NASA mission currently planned for launch around 2029, with arrival at Venus approximately 2 years later. It consists of 2 main components: a carrier spacecraft that will study Venus from orbit, and a descent probe that will drop through the atmosphere, sampling its composition as it falls. The descent will take roughly an hour. During that hour, the probe will pass through the entire atmospheric column, from the cool upper hazes down through the thick, hot lower atmosphere, all the way to the surface. It will be measuring as it goes. The measurements that matter most for our story are the noble gas abundances and the isotope ratios. Noble gases, helium, neon, argon, krypton, xenon, are chemically inert. They do not participate in geological or atmospheric chemistry. They just sit there. And because they just sit there, their relative abundances preserve information about where Venus's atmosphere came from and how it evolved. Different sources of atmospheric gas, volcanic outgassing, cometary delivery, solar wind capture, leave different noble gas signatures. By measuring these signatures precisely, Da Vinci can help determine how Venus's atmosphere was assembled and how it has changed over time. And then there is the DH ratio. Da Vinci will measure it with far greater precision than Pioneer Venus achieved in 1978. That earlier measurement established the basic enrichment, roughly 150 times Earth's value. But the uncertainty was significant. A more precise measurement will tighten the constraints on how much water Venus lost and over what timescale. Will Da Vinci tell us how Venus spins? Not directly. But it will tell us about the atmosphere's history, and the atmosphere is intimately connected to the spin through thermal tides. A better understanding of how the atmosphere evolved is a better understanding of the forces that shape the rotation. The probe is targeted at Alpha Regio, a highland region that may preserve some of Venus's oldest exposed surface material. In the final minutes of descent, cameras will image the surface at high resolution. If the rocks in Alpha Regio are compositionally different from the basaltic plains that cover most of Venus, it could suggest they predate the global resurfacing event, a window into an older Venus. The second mission is Veritas. Veritas is also a NASA mission, planned for the early 2030s. Where Da Vinci focuses on the atmosphere, Veritas focuses on the surface and the interior. It carries a synthetic aperture radar far more capable than Magellan's, along with instruments to map the planet's gravity field and surface composition. The radar will image the surface at resolutions approaching 15 meters, roughly 10 times better than Magellan. At that resolution, geological features that were invisible in the 1990s data will become visible. Fine-scale volcanic structures, tectonic features, possibly even evidence of ongoing geological activity. The gravity mapping is equally important. By tracking tiny variations in Veritas's orbital speed, scientists can map the gravitational field of Venus in detail, and from that, infer the structure of the planet's interior. Where is the crust thicker? Where is it thinner? Are there plumes of hot material rising from the deep mantle? Is the interior structure consistent with a catastrophic resurfacing event? Or does it suggest a more gradual geological history? Veritas will also carry a near-infrared spectrometer that can peer through atmospheric windows, specific wavelengths where Venus's atmosphere is partially transparent, to measure the composition of surface rocks. This is something Magellan could not do. If Veritas can identify regions with different rock compositions, it could reveal geological diversity hidden beneath the apparent uniformity of the radar images. The third mission is Envision, from the European Space Agency. Envision is designed to study the connections between Venus's atmosphere, surface, and interior. Where Da Vinci focuses on atmospheric chemistry and Veritas on surface geology, Envision aims to understand how these systems interact. How does volcanic activity affect atmospheric composition? How do atmospheric processes affect the surface? What is the current state of Venus's geological engine? Envision carries a radar sounder that can penetrate the surface and image subsurface layering. It potentially reveals buried geological structures from before the resurfacing event. If ancient terrain survives beneath the lava plains, Envision might detect it. Together, these three missions will provide the most comprehensive picture of Venus we have ever had. Atmospheric chemistry from Da Vinci, surface geology and interior structure from Veritas, system-level connections from Envision. But we should be honest about what they will and will not resolve. They will almost certainly narrow the range of plausible spin histories. A precise DH ratio constrains water loss models. Detailed gravity maps constrain interior evolution models. Surface composition maps may reveal pre-resurfacing geology. Each of these narrows the field. They will not, in all likelihood, uniquely determine how Venus came to spin backward. The observational degeneracy that Correa and Lasker identified is structural. It cannot be broken by better measurements of the present state alone. It requires information about the initial state, information that may no longer exist in any measurable form. What these missions will do is transform Venus from a planet we have a handful of measurements of into a planet we understand as a system. And within that system-level understanding, some spin histories will become less plausible, and others more so. The field of possibilities will shrink, even if it does not collapse to a single point. The data is coming. Not tomorrow, not next year, but within the next decade, 3 spacecraft will be at Venus simultaneously, and the planet that has guarded its secrets so effectively will face the most sustained scientific interrogation it has ever experienced. Whether it will answer is another question entirely. Before we begin to close, it is worth acknowledging that the ideas we have discussed so far, tidal spin down, giant impacts, atmospheric coupling, are the mainstream explanations. They are the ones with the most mathematical support and the broadest acceptance in the planetary science community. But they are not the only ideas that have been proposed. One recurring proposal is the Planet 5 hypothesis. The idea that an additional planet once existed in the inner solar system, orbiting between Mars and Jupiter, or perhaps between Earth and Venus. If such a planet existed and was later ejected or destroyed through gravitational interactions, its presence during the early solar system could have perturbed Venus's orbit and spin in ways that the current 4-planet inner solar system does not predict. There is no direct evidence for Planet 5. It is invoked to explain several features of the inner solar system that are otherwise difficult to account for, including the late heavy bombardment, a period of intense cratering roughly 3.9 billion years ago. Whether it could also explain Venus's rotation is speculative, but the idea has a certain elegance. If the inner solar system was once configured differently than it is today, then the initial conditions we use for Venus's spin models might be wrong in ways we haven't considered. Another idea involves chaotic resonance capture. In the early solar system, when the planets were still settling into their final orbits, gravitational interactions between them could have temporarily locked Venus into spin-orbit resonances, states where the planet's rotation period is a simple fraction of its orbital period. If Venus passed through several such resonances as conditions changed, the cumulative effect on its spin could have been significant and difficult to predict, because chaotic dynamics are, by definition, sensitive to initial conditions. The resonance idea gains a certain plausibility from the fact that Venus and Earth do seem to share a near resonance today. Every time Venus reaches inferior conjunction, its closest approach to Earth, it presents very nearly the same face toward us. Whether this is a meaningful dynamical relationship or a coincidence remains debated, but it hints at a gravitational conversation between the two planets that may have been louder and more consequential in the distant past, when orbital parameters were different and the inner solar system was more crowded and chaotic. There is also the possibility that Venus was tidally locked early in its history, spinning once per orbit with one face permanently toward the Sun, and then later knocked out of that state. Tidally locked planets are common in other star systems, and the early solar system's gravitational environment was more chaotic than it is today. A tidally locked Venus disrupted by a passing body or a resonance with another planet could have ended up spinning slowly in either direction. The tidal locking then release scenario carries a particular appeal because it sidesteps the question of how Venus's spin was reversed. In this picture, the spin was never reversed. Venus simply stopped, locked in place by the Sun's gravity, and then some perturbation, perhaps a shift in atmospheric mass or a change in orbital eccentricity, broke the lock and allowed the planet to drift into slow retrograde motion. This drift occurred under the influence of the atmospheric thermal tide. The reversal, in other words, would have been less a dramatic crossing of zero and more a gentle release, like a held breath finally let go. The difficulty is that tidal locking requires specific conditions of orbital eccentricity and internal dissipation that we cannot confirm for early Venus, and the mechanism that would break the lock remains speculative. And at the most speculative end of the spectrum, some researchers have considered whether conditions in the protoplanetary disk itself, the cloud of gas and dust from which the planets formed, could have imparted unusual spins to forming planets. Eddies and turbulent flows in the disk might have delivered angular momentum from the beginning. Under this scenario, Venus has always spun backward. It did not reverse. It was born this way. None of these ideas are considered likely by the majority of researchers. They lack the quantitative support of the tidal and impact models. They introduce additional unknowns without clearly resolving existing ones. But they serve an important purpose. They remind us that the space of possible explanations is larger than the space we have explored in detail. They keep the question open. And in a field where the mainstream explanations already admit fundamental degeneracy, where we cannot distinguish between two well-supported histories using present-day observations, a little humility about the completeness of our inventory of ideas seems appropriate. We have spent a long time with Venus now. We have traced the physics of tides and the violence of impacts. We have watched atmospheres thicken and oceans evaporate. We have followed the mathematics of spin into a place where two roads converge and the trail markers vanish. It is worth pausing here to consider what Venus has actually taught us. Not about planetary rotation, though it has taught us that too, but about the nature of scientific knowledge itself. Venus is sometimes described as Earth's twin. Similar size, similar mass, similar distance from the Sun, similar bulk composition. And yet its surface conditions are radically different. 450 degrees Celsius, 90 atmospheres of pressure, sulfuric acid clouds, no liquid water, a day longer than its year, backward rotation. The divergence between these two planets is one of the most important unsolved problems in planetary science, and the spin question sits at the heart of it. Because the spin affects the climate affects the geology, and the geology affects the atmosphere. Everything connects, and the thing we understand least, how and why Venus rotates the way it does, may be the key that unlocks or permanently locks the rest. There is a concept in geology called a palimpsest. It comes from the world of manuscripts. A palimpsest is a parchment that has been written on, scraped clean, and written on again. The original text is gone, but sometimes faint traces survive. Scholars with the right tools and the right light can occasionally recover fragments of the erased text. Venus is a planetary palimpsest, and like a true palimpsest, the act of rewriting has itself become part of the story. Each volcanic resurfacing event, each epoch of atmospheric evolution, each slow adjustment of the rotation rate has deposited its own thin layer of information while destroying the layers beneath. The planet we observe today is a composite, a geological collage assembled from fragments of different eras, none of them complete. Reading Venus is less like reading a book and more like studying a wall that has been painted over 100 times. The color you see tells you about the most recent coat, but says almost nothing about the 50 coats beneath it. Its original geological text has been scraped away by global volcanism and rewritten in basalt. Its atmospheric composition has been altered by billions of years of chemical processing. Its magnetic history, if it had one, was never recorded in a medium that survived. The original manuscript, the one that would have told us about the first billion years, about the spin Venus was born with, about the events that shaped its early rotation, that manuscript has been overwritten. And here is the question that Venus forces us to confront. Can we read the original text? Or has it been too thoroughly erased? In most areas of science, we operate on an implicit assumption that enough data, gathered with enough care, will eventually resolve any question. This assumption is not naive. It has been validated over and over. Questions that seem permanently mysterious, the composition of stars, the age of the universe, the structure of DNA, yielded to sustained investigation. But Venus suggests a limit. Some histories may be genuinely unrecoverable. Not because we lack the technology, not because we lack the funding, not because we lack the cleverness, but because the information itself has been destroyed. The universe is not obligated to preserve evidence of everything that happened in it. Physical processes can erase information as thoroughly as they create it. This is not a comfortable idea. Scientists are, by temperament and training, optimists about the knowable. The whole enterprise of science is built on the conviction that the natural world is comprehensible. And it is. But comprehensible does not mean completely reconstructible. We can understand the processes that shaped Venus without being able to determine uniquely and definitively which specific sequence of events produced the planet we observe. And this brings us to exoplanets. In the last 3 decades, we have discovered thousands of planets orbiting other stars. Some of them are Venus-sized. Some orbit in their star's habitable zone. Some may have atmospheres we can characterize with the James Webb Space Telescope and its successors. When we characterize those atmospheres, we will be trying to reconstruct the histories of worlds we can barely see. We will be inferring surface conditions from spectral lines. We will be guessing at geological histories from atmospheric compositions. We will be doing, at interstellar distances, what we have struggled to do for a planet 40 million kilometers away. The James Webb Space Telescope has already begun this work. By analyzing starlight filtered through the atmospheres of transiting exoplanets, Webb can identify the chemical signatures of gases like carbon dioxide, water vapor, and methane. Future missions and future telescopes will push further, measuring atmospheric densities, constraining surface pressures, and perhaps even detecting the rotational signatures of distant rocky worlds. When that data arrives, we will reach for our models of atmospheric tides, of core mantle friction, of gravitational torques, all the same tools we have built by studying Venus. Every lesson Venus has taught us about the relationship between atmosphere and spin will become a lens through which we interpret planets we will never visit. If Venus, our nearest planetary neighbor, a world we have visited with spacecraft, mapped with radar, sampled with probes, can erase its history so thoroughly, what hope do we have elsewhere? What hope do we have of reconstructing the histories of planets we observe as a slight dimming of a distant star? The answer is that we have exactly the hope we should have. Measured hope, calibrated hope, the kind of hope that knows its own limits. Venus teaches us to be careful about what we claim to know. It teaches us that understanding a planet's present state is not the same as understanding its past. It teaches us that some questions may have ranges of answers rather than single answers, and that publishing a range is more honest than publishing a guess. And Venus teaches us something else, something quieter, that a question worth asking is still worth asking even if it cannot be fully answered. The effort to understand Venus's rotation has produced real knowledge, deep insights into tidal physics, atmospheric dynamics, impact mechanics, and the limits of planetary reconstruction. The question has been productive even in its irresolution. Scientists sometimes call this posture productive irresolution, the willingness to hold a question open, to resist the urge to collapse uncertainty into a premature answer, to let competing hypotheses coexist without forcing a verdict. It is not indecision, it is discipline. The slow physics model and the giant impact hypothesis and the exotic alternatives all remain in the conversation, because none of them can be ruled out with the evidence we currently possess. Choosing one prematurely would mean ignoring the others. The honest position, the scientifically rigorous position, is to carry all of them forward, testing each against new data as it arrives, refining the models, narrowing the possibilities, and accepting that the narrowing may take decades or centuries. The question is not weakened by remaining open. It is strengthened. Every year that Venus resists a simple answer is a year that deepens our understanding of how many ways a planet can become what it is. Some questions are not doors to be opened, they are windows to look through. And the view through the window of Venus's rotation is a view of how planets work, how solar systems assemble, and how much of history is written in fading ink. Venus has been spinning the wrong way for 4.5 billion years. It has not sped up. It has not slowed down appreciably. It has not explained itself. It just turns, once every 243 Earth days, in the opposite direction from nearly every other object in the solar system, with the composure of something that has nowhere to be and nothing to prove. We have spent this time together examining the question of why. We have looked at solar tides, patient and relentless, pulling at a planet's spin over geological time. We have considered giant impacts, the collisions of world-sized objects in a young and crowded solar system. We have traced the coupling between a thick atmosphere and the solid planet beneath it, a feedback loop between wind and gravity that may have guided Venus to its present slow rotation. And we have found that more than one of these stories fits the evidence, that Venus's present state, measured with great precision, does not uniquely determine its past, that the planet has erased much of its own history through volcanic resurfacing and atmospheric processing, that the question, why does Venus spin backward, may belong to a category of scientific questions that admit ranges of answers rather than single, definitive ones. Science has not failed here. Understanding the limits of what can be known is itself a finding, and a valuable one. Understanding the limits of what can be known is itself knowledge, and it is knowledge of a particularly important kind. It tells us something about the relationship between a universe that changes and the records it leaves behind. There is something reassuring in a question that refuses to be rushed. We live so much of our lives in the tempo of answers, the quick retrieval, the instant summary. But Venus has been spinning backward for longer than complex life has existed on Earth, and we have been watching for only the width of a single human lifetime. The mystery does not mind our slowness. It will wait for better instruments, for missions not yet funded, for graduate students not yet born. And that waiting is not failure. It is the quiet, honest shape of discovery when the subject is large enough to deserve it. Data is coming. Within the next decade, 3 spacecraft will orbit or descend into Venus, carrying instruments designed to measure what previous missions could not. They will refine the DH ratio. They will map the surface at 10 times the resolution of Magellan. They will peer beneath the volcanic plains with radar sounders. They will measure noble gas abundances that constrain the atmosphere's origin. These missions will not solve the spin question. We should be honest about that. But they will change the shape of the question. They will make some histories less plausible and others more so. They will turn a wide-open mystery into a better constrained one. And in science, constraining a mystery is how progress is made, one measurement at a time, across decades, across centuries. There is something worth noticing about the simplest questions. Why does the wind blow? Why is the sky blue? Why does Venus spin backward? They sound like questions a child would ask. And they are. That is what makes them so difficult. They do not come preloaded with assumptions. They do not narrow themselves to a manageable scope. They just ask. And the universe, under no obligation to make its answers simple, responds with all the complexity it has. The simplest questions carry the most patient answers. Venus will be there tomorrow evening if the sky is clear. A bright point of light in the west, setting slowly after the sun. You can find it without a telescope. You can watch it without knowing anything about tidal torques or atmospheric superrotation or deuterium to hydrogen ratios. If you are near a window tonight, or if tomorrow evening the sky is clear, you might step outside and look toward the west just after sunset. Venus will likely be there, that steady cream-colored point that does not flicker the way stars do. Just your eyes and a few minutes of stillness. What you are seeing is sunlight reflected off the top of that thick carbon dioxide atmosphere, the same cloud deck that hid the planet's surface for so long. And beneath those clouds, right now, the ground is turning so slowly that you could walk fast enough to keep pace with it. 1 degree every 40 hours or so. The whole planet drifting through its backward day like someone turning over in a very long sleep. And perhaps there is a kinship in that. Sleep, after all, is its own slow rotation, a turning away from the noise and the light. Your breathing changes. Your thoughts loosen and drift. The questions that seemed so urgent an hour ago settle to the bottom of your awareness like sediment in still water. You do not solve them by sleeping. You simply let them rest. And sometimes, in the morning, they look different, smaller or clearer, or rearranged into something you hadn't expected. But if you do know those things, even a little, the light looks different, not brighter, not more beautiful, just deeper. A point of light with 4.5 billion years of unresolved history behind it, spinning the wrong way, in no hurry to explain. So let the questions be. Let Venus keep its secrets for one more night. The spacecraft will go when they go. The data will arrive when it arrives. Tonight, you are not solving anything. You are just here breathing, in a warm place, on a planet that spins in the usual direction, at a speed that gives us reasonable days and ordinary nights. And that is more than enough. The stars outside your window are not waiting for you to understand them. They are just shining, the way they have for billions of years, patient and indifferent and beautiful. You can look at them tomorrow. You can learn their names next week or never. They will still be there. Thank you for spending this time with us. If you're still here, you've earned this quiet. Venus will keep turning. The spacecraft will launch. The data will arrive. And some night, a few years from now, someone will publish a paper that narrows the possibilities just a little further. Not a final answer, just a better question. That is how it works. That is how it has always worked.